Okay, so in this particular problem, we just calculated that if we started up here at rest, then we'd have a velocity of 12.5 at the bottom. Okay, all right. Well, what if this was in real life? So what if, for example, this was a roller coaster, you went to the amusement park and you predicted that at the bottom your speed would be 12.5. If you took out your speed gun and actually found the speed, would it be 12.5?
No.
No. Okay, would it be faster, slower? Slower. Okay, because we're ignoring a big component, which would be friction. All right? So in this particular problem, I would ask you something like this. Well, how much... let me actually add to this. Let's say assuming, so you took out your speed gun, assuming the V final is actually 10, how much energy was lost? Or how much, in this case, you can't technically ever lose energy, right? It has to be conserved, but let's say how much mechanical energy is lost. Okay? Or another way I might ask this question, I might say something, well, where's that energy going? Why is it lost? What's happening? There's friction involved, right? And friction is going to do work. So another way I might ask this question is how much work is done by friction? Or another way I could ask this question is thinking about where the energy is actually going. So friction's doing work, but what's friction turning mechanical energy into? Into thermal energy, right? So another way I could ask this is how much thermal energy or heat energy is generated, or we often say dissipated. So anyway, I'm just saying, I'm asking these three different ways because you'll see it in these three different ways, or something similar to this, where they either ask how much energy is lost, how much work was done by friction, or how much thermal energy is dissipated. Okay, but they're asking for the same exact thing in all these cases. So how are we going to figure that out?
Find the kinetic energy of both the velocities, and then you subtract the theoretical by the actual.
Okay, so we're going to go E initial equals E final, right? Sounds like you guys are on the right track. So what kind of energy did we have at the very beginning? Potential. And how much energy are we going to have at the very end? Kinetic, right? And this is what you just did. You did this, UG equals KE, and you found a VF to be 12.5. Well, we're saying the VF is not 12.5, which means this is going to be less than this. So we're just going to add the term here. We'll say plus, so we're going to start with a certain amount, right? It's going to turn into kinetic, but there's going to be something left over. So you could add whatever you're going to call this. You could call this E lost, or we could call this work of friction, or, remember the symbol that you used back in chemistry for heat energy, thermal energy? Two. Okay, so whatever you're going to call it, you're just solving it the same way. So go ahead and do it. Why don't you guys go ahead and do it? Can we cancel the masses like we almost always do? No. So it's not in all three terms. Be careful. This is a very common mistake. Just blindly canceling masses. You cannot do that here. Someone that did this, what are you getting for that starting initial energy? So we started with 156.8. Good, confirmed. And then how much kinetic do we end up with? Okay, so I wrote it like this just so you can see the concept and play with understand the concept. So we started with 156.8, right? And then we ended up with 100 joules. So how much energy got lost? The difference between those two, right? So the work done by friction, or the energy lost, or the thermal energy gained, okay, in this problem would be 56.8 joules. All right. Let's keep going. Let's add to this question. So let's say this letter B. Letter B I'm going to ask you is, what is the average force of friction? In letter C, what is the coefficient? What's the kinetic coefficient of friction? So I do need to give you some more information. So let's say that, yeah, there's lots of things I could give you. I'm going to give you this distance from here to here. Right? So again, I want to give you a few minutes, see if you can solve this one on your own. So just make sure we're on the right track. If we know the work of friction, how do we find the force of friction? Work equals force times distance. Yep. So what distance am I going to use? Am I going to use 8 or am I going to use 10? Neither. What am I going to use? The hypotenuse. Good. So you have to use, so remember, it's not just force times distance, it's force parallel to distance. So the force here is going along the ramp, right, parallel to the ramp. So you have to make sure you use that distance that is a distance of the ramp. So just use your Pythagorean theorem, right, a squared, 10 squared, c squared, what's the answer? 12.8 meters, yeah. Someone got the answer? 4.4. How are we going to find mu? So what's the basic equation for friction?
Normal times
Mu times normal. Okay, so what's the normal force for an inclined plane? mg cosine theta. Yes, you remember for inclined plane you have to do your break it up. So okay, mg cos theta. So if you wanted, you could calculate the angle first, right, and then plug that into cos theta. You actually don't have to calculate the angle if you don't want to, because we know cos theta equals adjacent over hypotenuse. So if you don't want to calculate, if you want to save yourself a step, right, you could just know this and just plug that into here. So I'm going to do it like that. If you don't feel comfortable with this, that's fine. Just find the angle first and then cosine the angle. And we'll all get the same answer. What are you guys getting?
0.229.